In this episode, the world's deepest production and drilling platform.
What we do is like the space program in the other direction.
Pushing engineering frontiers further than ever before.
These machines can easily work at 10,000 foot depths or greater.
And the groundbreaking innovators of the past.
What once was the wall has now become the floor.
So the Intumescent Paint now is charring due to a chemical reaction
That made the impossible possible. Since the 1940s, the Gulf of Mexico has provided a vital source of energy for the US. Almost 2 million barrels of liquid fuel are produced there a day. And almost half of the country's entire petroleum refining capacity is on the Gulf Coast.
The importance of oil and gas in the world economy is paramount. I mean, energy makes the world go round. You know, ever since the invention of fire, that's what's driven our civilization and our economies forward. You know, we're going to transition to whatever the fuels of the future are. In the meantime, oil and gas is a bridge to those new technologies and keeps us moving forward as a human race.
As the search for fuel in the Gulf of Mexico extends ever further and ever deeper, engineers face their biggest ever test.
The challenge of accessing deep water reserves gets harder and harder. We're exhausting the supply or access to the easy barrels. And with every new discovery and development, it gets more challenging and it gets deeper. That's what causes us to push the frontiers of technology.
300 kilometers from shore, at the vanguard of that engineering innovation, is the Perdido. The deepest production and drilling facility in the world. A $3 billion engineering colossus.
The structure itself stands as tall as the Eiffel Tower, from the bottom of the Spar all the way up to the top of the drilling rig. And it's floating there in 8,000 feet of water, designed to accommodate hurricane-force winds, what we call the 1,000-year storm. To give you a sense of how much Perdido contributes, one day's production from Perdido could power 500 cars for 15 years.
At 55,000 tons, the world's largest floating production and drilling structure is anchored to the seabed by 9 3-kilometer-long steel and polyester mooring lines. Where oil and gas from 35 newly discovered wells, some as far as 11 kilometers away from the platform, is pumped to the surface. A 170-meter-long, 36-meter diameter floating spar provides the base for the 3 decks where the oil and gas are processed. There's space for 2 helicopters, a restaurant, fitness room and cabins to house the crew of 150 plus that live and work on the record-breaking platform for 14 days at a time. It's an engineering achievement once thought impossible.
You were going into a frontier area in what we called the ultra-deep water. We were going in reservoirs that had not truly been tested before in new plays for the oil and gas industry in the Gulf of Mexico. You were going into one of the most severe environmental conditions as you can imagine in 7,800 feet of water.
Making Perdido possible would take a giant technological leap. Oil and gas fields wouldn't exist without the death of tiny plants and creatures. While dinosaurs roamed the earth, gazillions of dead plankton and algae built up on the seabed. Before a crust of rock formed over the top. Millions of years of pressure and the Earth's heat essentially cooked this into an energy-rich soup. But getting to it under the water isn't always easy. Operating at a never-before-attempted almost 2,500-meter depth meant it would be impossible for Perdido to have legs like a standard oil rig.
The reason we couldn't use a conventional tension leg platform was because the water depth was so great that those tension legs would be too heavy for any structure to be able to support.
To find a futuristic solution, Perdido's designers would have to draw on technology pioneered in the past. A clue to how the Perdido team have conquered the deep can be found in San Diego, California. Mechanical engineer Dan Dickerell is getting a rare opportunity to explore one of history's most unique vessels.
In the early 1960s, the U.S. Navy was looking for a new type of research platform from which to take precise underwater acoustic measurements. Now, the submarines they'd been using previously were deemed unstable due to their shape. They would yaw in the water, making it impossible for the scientists on board to take the precise measurements they needed.
Oceanographer and underwater explorer Fred Speece was the man tasked with coming up with a solution.
After months of testing various designs, Speece and his team came up with this, the RP Flip, or Floating Instrument Platform.
But Flip earns its name in another quite extraordinary way. Believe it or not, Flip is not sinking.
It's one of a kind, a 108-meter long spar buoy that can go from horizontal to vertical in around 30 minutes. It's such a cool piece of engineering.
First, the platform is towed to where it will operate.
During the flip itself, everyone stands out on the outside decks. As the process occurs, the decks and the bulkheads exchange places throughout the horizontal to vertical transformation. Most rooms on board have two doors. One, horizontal orientation, and another door for the vertical orientation of the platform. Now, in the configuration it is right now, we're in the horizontal position. And imagine what happens when the flip occurs. What once was the wall has now become the floor. And what once was the floor has now become the wall.
Everything on the flip is designed in two configurations.
Look at this. It's a sink. It's a bathroom sink. But, oh, it pivots. How bizarre is that?
From rotating condiment racks in the galley to tables on the walls.
To maintain its stable position in the horizontal, there are huge concrete blocks underneath what is now the floor. But when it's time to change and flip from horizontal to vertical, tons of seawater are pumped into those ballast chambers slowly. That changes from horizontal to perfectly vertical. It's so cool.
The science behind Flip is as simple as it gets.
The genius behind how the flip operates is its ability to sink in a controlled fashion. Here I have a plastic bottle that's going to represent the flip. Now, I've taped some washers at the bottom to help with stability when we make the transition from horizontal to vertical. If I place it in the water, we can see it floats in a horizontal configuration as we would expect. As I fill the bottle with water, what we're going to do is going to have a transition from horizontal to vertical.
When flipped vertically, amazing stability is provided by the 700 tons of water ballast in the long spar sitting below the surface. It's so steady that Flip is capable of dealing with swells up to 25 meters high. And to rotate back to the horizontal, compressed air is simply used to force the water out, turning the platform back into a more familiar ship mode.
These huge generators can also pivot by design.
It's testament to the brilliant design of Fred Spiess that this amazing research vessel
This is like being in a carnival funhouse.
is still in use, more than half a century after it was launched.
Oh, this platform is too crazy.
In order to create a stable platform in depths of nearly 2,500 meters, Perdido's engineers take the principle behind the flip and in 2006 in Finland, begin building the world's biggest floating spar.
The spar itself is constructed quite ingeniously. It's done in slices. You cut it into slices. And it's from the top of it, you do the can section, and then the truss section you do. And then it's welded together, slice by slice.
Each of the 7 ring sections has 12 compartments, each self-contained. So if disaster strikes and a compartment is punctured, then only that compartment would take on water. On the end of the giant can-like section, an open truss of pipeworks and ballast area is added to complete the unprecedented structure.
Perdido's spar is about 550 feet. In diameter, it's 118 feet.
In 2008, the spar is delivered to the Perdido site in the Gulf of Mexico.
It's a key milestone for us because the spar is actually in its most vulnerable position when it's floating horizontally. So as soon as we can get it up to the vertical position, then it's in the position that it's designed to operate in, and it can withstand storms better.
Plugs are pulled to let in seawater. And then, like Fred Spiess's flip ship, the spar slowly begins the process of switching from horizontal to vertical.
So they also pump water into the tanks inside the can section, and that lowers it to give it that stability, to allow the pitch and the roll to stabilize.
Once upended, the spar must be secured, as storms or so-called tropical disturbances are on their way.
We have a long duration, relatively long duration before we can get to storm safe. The first disturbance is predicted to be here within about 7 to 8 days.
9 supersized mooring lines must tether the floating spar to the seabed. A total of more than 30 kilometers of chain and rope.
So what we do in order to secure the structure floating on the surface is we connect the suction anchors on the seafloor with 2-mile-long, huge polyester mooring lines, about 25 inches thick, and about 300 meters of massive steel chains on either side of the mooring line.
For maximum protection from storms, the lines fan out for more than 2.5 kilometers around the spar.
Now it's still sitting pretty high in the water, so they put a weight in the bottom, essentially iron ore. They pump into a tank at the bottom of that truss section, so you have a lot of weight at the bottom tank.
With the additional weight in the mooring lines, the spar is storm safe. But this is merely the beginning of the process of creating the world's deepest production and drilling facility.
It was critical to get the topsides to be a certain weight because we wanted to do the topsides installation with a single lift.
And its engineers will need to draw from more brilliant historical breakthroughs.
Oh, look, there's another arm right there. I could use both of them. It's like right out of like some cyborg thing. Whoa. It's making noises.
To deliver their record-breaking feat of impossible engineering. 300 kilometers off the Texas coastline in the Gulf of Mexico, the Perdido platform marks a new frontier in ultra-deep water operations. Moored in waters nearly 2.5 kilometers deep, the rig extracts oil from 35 wells across 3 brand new oil fields, producing 100,000 barrels of oil each day. Creating a rig like this calls for daring engineering. Having anchored the world's biggest spar, the next step is fitting the all-important topside.
What we call the topsides is all of the equipment that sits on the structure in the water that allows us to produce the oil and gas. It was critical to get the topsides to be a certain weight because we wanted to do the topsides installation with a single lift in the interest of doing it efficiently and safely.
Traditionally, these multi-story mega plants are assembled at sea, but a location as remote as Perdido's calls for a different solution.
The topsides were constructed in Ingleside, Texas, and they were done 1 layer at a time, like a birthday cake, and there are 3 layers on the deck of Perdido. All that was done in the construction yard, and then you had a heavy lifting device that took that entire 3-deck layer and put it on a barge and shipped it offshore.
With the final weight remarkably under 10,000 tons, in August 2008, the topside begins its journey deep into the Gulf of Mexico, where the giant crane vessel the Thialf is waiting to begin the biggest single lift ever attempted in the Gulf of Mexico. After 5 years of construction, this was the moment of truth, combining both spar and topside.
Remember, these things, they are built separately, one in Finland and one in Texas, and all by measurements, and all of a sudden, this is the first time they said things better mate together. And there's a lot of very anxious moments as that crane is lifting that topsides onto that hull.
As the lift begins, the topsides are pivoted into position, fitting perfectly.
To see those pins go in, it's a wonderful feeling.
And the spar settles into its new draft. With this mammoth milestone complete, the Perdido team must focus on installing production equipment on the seabed. But nearly 2,500 meters below the surface, with a terrain resembling a mountain range, it is a seemingly impossible working environment.
The conditions at the water depth at Perdido and 7,800 feet of water, it's extreme amount of pressure. In addition to that, it's really, really cold down there. So you're talking temperatures in the order of 38 degrees Fahrenheit. So very, very cold, and there's no light. So it's very hostile conditions in terms of the pressure that we have down there.
With sophisticated deep-sea hardware needed on the seabed, physically interacting with it is impossible.
You just can't get people down there. Yet a considerable amount of work has to still be done at these water depths.
In an environment where even fish struggle to survive, how do you carry out some of the most advanced engineering work on the planet? It's a problem that requires another ingenious innovation from the past. The 1950s America was at the forefront of developing nuclear power for peacetime use. Crucial to this movement was Chicago's vast Argonne National Laboratory. With special access, Professor Eric Lima has taken to 3 wheels to explore this extraordinary 1,500-acre site.
It's very cool.
Discovering how this era of hazardous research spawned a game-changing innovation.
This absolutely enormous laboratory was used to test the actual materials coming out of the reactors. Now, of course, those materials are highly radioactive. So how can technicians manipulate those materials without exposing themselves to radioactive contamination? That was the challenge.
Toxic substances were initially handled through sealed glove boxes, but even these posed safety concerns. To further distance scientists, engineers drew on a centuries-old technique based around a device known as a pantograph.
The principle is a master-slave relationship. Now, this was developed in the 1600s, and what happens is that any movement of the master pen is transferred along the wood to the slave pen. And so you can trace diagrams, like I'm about to do with this radioactive symbol, and that tracing can actually be amplified. And so here it is, the original and the drawing.
Using this principle, early mechanical master-slave manipulators, MSMs, allowed technicians to transfer basic movements to a second arm from behind the safety of a glass wall. But their dexterity and strength was still limited. In 1954, engineer Raymond Goertz looked beyond the purely mechanical, adding a motor to each arm, connected by an electric cable.
And so what they would use are these incredible arms. And this is really cool. Look at this. On the other side of that glass, it does exactly what I do. And not only does it move back and forth, in and out, but check this out. Look at this. That arm right in there exactly mimics my actions. Cool. And then it's actually a force multiplier. So I could pick up something very heavy, just like I was gripping it with my hand, and move it over. Well, look, there's another arm right there. I could use both of them. It's like right out of like some cyborg thing. Whoa, it's making noises. That's the servo motors up there.
The motors not only multiplied force, they also allowed the operator to feel the movements. Improved precision was matched by greater flexibility, and the electrical cable connection allowed engineers to separate the master and slave arms.
Goertz was able to decouple the arms, and what that means is they can be as far apart and in any location that we want. So we could actually have the slave arm coming up from the floor or coming at some weird angle to get us right where we want it to go.
Over the following decades, Goertz's remote technology was further finessed, producing a series of telemanipulators that combined safety with robotic precision.
Woo!
If in the right hands.
Whoa! As you can see, it's not as easy as it looks. So thanks to Goertz and his work at Argonne National Laboratory developing these telemanipulators, we are able to go as humans in places that we've never been able to go before.
Resembling a scene from a sci-fi novel, engineers at Perdido are using telemanipulator technology to work at depths that were once thought impossible. This fleet of remote-operated vehicles, or ROVs, sweep the ocean bed that lies almost 2.5 kilometers beneath the platform.
This is exactly the type of ROV that we would use on Perdido. This is a 1,000-pound thrust machine, and one of the main reasons we use them is simply because below about 600-foot water depth, it gets really, really dicey, really, really risky to have humans at those depths enter the ROV. These machines can easily work at 10,000-foot water depths or greater, and we can always get them back, and they never get hurt.
These sub-aqua robots are equipped for serious work.
These are our hands to actually connect and attach all the different equipment we need. And here is our eyes. This camera, this high definition camera, is how we see what we have going on down there.
A leap forward from Gertz's telemanipulators. These ROVs can be operated via a joystick using a fly-by-wire system that originates on board the rig.
The way these machines operate, they're actually tethered back to Perdido. Is actually an umbilical line that runs the entire water depth, all 7,800 feet. And from there, there's an additional 600 feet or so of umbilical that allows the ROV to fly out on excursions and move about the well pattern to go from one well to the next so they can survey the entire subsea system.
Installation, drilling, and maintenance can all be achieved remotely. But there was one ROV-driven task that would be the crowning glory of Perdido's success.
So you're 150 miles offshore of the coast of Texas, and you had to get that oil and gas back to the beach. Most of the oil pipelines that you have in the Gulf of Mexico start in the less than 5,000 feet of water depth. So we had to connect from Perdido's location to oil pipelines and gas pipelines that are further up in the shallower water.
Connecting to a live export line at these depths had never been attempted. The pipe must be cut and connector installed with millimeter precision. And at nearly 1,500 meters, it was completely out of human reach. Over a 2-year period, the Perdido team designed and rehearsed an ROV-driven system. When they eventually made the attempt, it worked perfectly.
To be able to do all that with remote-operated vehicles. And the water depth that they did that at Perdido was world-class, never been done before.
This state-of-the-art solution is opening up the depths of the ocean. But to tap into the world's deepest oil reservoirs, Perdido's engineers will need to look to the past.
The moment I flip this switch, something very exciting is going to happen.
To produce more impossible engineering. The Perdido platform is the deepest offshore production and drilling facility ever built, and has pushed the boundaries of offshore engineering. This deep-sea hub has 22 wells directly underneath its structure, and its reach is far greater. A further 13 wells across 3 oil fields, transporting crude through nearly 300 kilometers of pipeline web. But creating ultra-deep offshore wells is no easy task.
So when you're offshore, drilling's a little bit different than if you're on land. In Perdido's wells, the total well depth was somewhere around 17,000 feet. But almost half of that, 7,800 feet of it, was just the water column.
Not only are the reservoirs ultra-deep, they sit in a previously untapped ancient rock layer.
We were pushing the boundaries of not only technology, but actually a new frontier in terms of the geology of what we were tapping into. And there was a lot of excitement, uncertainty around how it was going to produce.
Each new well must be drilled with precision, keeping the water out and the oil in, or the project and the environment will be permanently damaged. To find a solution, engineers must look to the pioneers of the past. Andrew Smith has come to Titusville, Pennsylvania, to discover how one man's inspiration paved the way to black gold.
The moment I flip this switch, something very exciting is going to happen. Here it comes, you can see it. Pennsylvania crude.
Before the mid-1800s, salt brine was the area's biggest commodity. But efforts to extract it from the ground were blighted by another substance, a smelly black goo.
To begin with, oil was touted as a medicinal product, capable of curing burns, cholera, asthma, indigestion, and even blindness. But its smell and its healing properties were questionable. But the real breakthrough was when it was discovered that oil could be distilled to burn as fuel for lamps.
Sensing a fortune, engineers needed to get the oil out of the ground fast.
It was here, in the small town of Titusville, that the hunt for oil took off at a scale never before seen. And all because of one man's simple innovation.
In 1859, railway worker Edwin Drake gambled his life savings on a small stake of the newly formed Pennsylvania Rock and Oil Company.
Drake, as a stakeholder and now employee, was sent here to this very site where he began his search for oil. But early attempts were met with mixed results. So at the time, the practice in drilling was to use something called percussion drilling, where the drill is just hammered down through the soil until you reach your oil.
Drake had some success with his technique, but Titusville's water-sodden ground was scuppering his plans.
As you withdrew the drill, the problem would be that the water would rush into that space and contaminate the oil he was trying to pump out. To overcome this problem, Drake and his assistant Billy Smith came upon the idea of connecting lengths of cast iron pipe to encase the freshly dug hole, preventing the ingress of the water.
With the cast iron pipe in place, they continued to drill through this now watertight space, through the ground, the bedrock, and down to the oil reservoir. After drilling 69 feet, they waited.
Overnight, it happened. Clean oil had risen up through the pipe to a point which it could now be collected. Drake's plan had worked.
By the following year, oil wells using Drake's innovative technique had sprung up all over the region, producing several 100,000 barrels.
The nation's oil bonanza had begun, and huge fortunes would be made from what was once a smelly goo that was simply a nuisance.
In order to drill to unrivaled depths, Perdido's engineers have taken the principle of Drake's system 350 kilometers offshore. And like that first well in Titusville, one thing is crucial.
The processes for drilling are designed around keeping the oil in the pipe. So you start with big diameter pipes, and as you go deeper, you get smaller and smaller concentric sizes of pipe.
To begin, a hole's drilled for a conductor pipe. Another drill then bores a few hundred meters before a casing pipe is installed. This is followed by a smaller drill and casing, and the process is repeated until the reservoir is reached. But with a seafloor in part like the landscape of the Grand Canyon, being able to hit your target with the drill is no easy task.
Most of the locations that we have to drill are quite far away from the rig, and we have to use directional drilling techniques in order to get there. The scale that we're talking about, to be able to land a well in the exact place that we need it. If you were in a typical room, the thickness of a human hair from the ceiling all the way down to the floor, hitting a square inch, is the kind of accuracy that we're talking about.
To tap reservoirs spread across nearly 80 square kilometers of seafloor, GPS drilling motors guide the drill string within a foot of its target. In all, 35 separate wells are created, feeding 5 risers leading up to the rig. But for the engineering team, perhaps the biggest challenge of all is lifting the crude oil up these risers to the surface.
The reservoirs are low pressure, lower than you normally would find in the Gulf of Mexico. That required us to add energy to the system in order to get the produced fluids up to the surface. To do that, we had to pump. We had to use electrical submersible pumps. Well, these pumps don't like gas.
Normally, the gas, oil, and water are separated on the surface. But to bring Perdido's oil to the platform, engineers must remove the gas at source, 2.5 kilometers beneath on the seabed. At the base of each riser, a unit separates the components. The gas naturally ascends, and the liquid is pumped to the surface.
The engineering leap for Perdido was really in two areas. One was the depth of the water in which we were working. The other, and more significant, was first ever subsea processing.
After decades of innovation, in March 2010, the moment of first oil from the world's deepest offshore wells arrives.
We're all piped in via camera to the guys who are actually offshore doing it. And then you start watching the pressure in the pressure gauges. And you see the pressure start falling, meaning that it's starting to flow.
It's been a long road, boys.
You know, you've just done something that, in Perdido's case, nobody had ever done before. We were pumping and separating on the subsea floor from day one, and it all worked, and you know, that was incredible.
Perdido's engineers are succeeding in producing oil from deep within the Earth's crust. But to ensure this operation remains safe, engineers need to look to the past.
So the Intumescent Paint now is charring due to a chemical reaction and swelling and turning into a thick char.
To create more impossible engineering. In 2010, the Perdido oil platform began production, making it the first of its kind to operate in ultra-deep water depths of almost 2,500 meters. A team of 172 workers spend 2 weeks at a time extracting enough oil to fill more than 6 Olympic-sized swimming pools each and every day.
As you fly up to Perdido, it's 200 miles away from the coast. There's pretty much nothing around it. And it's almost a 2-hour flight on the chopper. And as you get into the range of where Perdido is, you see this monument to what's possible out in the middle of nowhere. And it's really satisfying to land on that and see what we've accomplished.
Perdido's isolation creates logistical challenges. It's a 24-hour boat journey. So whilst much of the resupplying happens by ship, the fortnightly turnover of staff needs to be carried out by helicopter.
We're flying these really large helicopters like this S-92 you have, which can hold up to 19 passengers, although we'll fly it with about 15 or 16. In the event that helicopter goes down, that's a lot of people that we need to take care of.
The Robert Training Center in Louisiana is where Perdido staff, along with other oil and gas workers, are trained for worst-case scenarios.
So we're training these people how to safely egress that helicopter should the unfortunate happen. In case it does go into the water, we want them to be able to get out of the helicopter and wait for survival.
But when you're potentially processing more than 100,000 barrels of oil a day, one hazard above all others is at the forefront.
Fire protection on an offshore installation is of paramount importance. We design for safety. It's the #1 thing we have to get right.
The worst thing that could happen on a rig or production facility in the event of a fire is it gets out of control. It gets to be very large and very catastrophic. In that event, we're going to abandon the facility. We're going to put people in lifeboats that they've been trained to use, and we'll put those lifeboats in the water and get people away from the fire and abandon the platform.
Fire isn't just a hazard for the workforce. A hydrocarbon blaze can reach such high temperatures it has the potential to deform or destroy even solid steel.
As we become more complex and remote with these types of developments, the safety systems that we need in order to support them become ever more critical.
So, how can you protect Perdido's vast surface areas against the threat of extreme heat? The solution, surprisingly, has its roots in historical show business. If, hundreds of years ago, fire safety expert Luke Bisbee visited a theatre like this, he might have been taking his life in his hands. Because oil lamps were used for lighting, curtains and fabrics were frequently set ablaze. In 1786, French chemist Joseph Gay-Lussac was tasked with fireproofing France's theatres following a string of tragedies.
Gay-Lussac set to work trying to find an invisible, non-toxic compound that he could use to coat fabric, curtains, and scenery. He began experimenting with boron, a compound now used in detergents and cosmetics. And to demonstrate how effective it is, I'm going to do an experiment. Here I have a stage, and it has two curtains. One of them has been soaked in boron solution, and the other one is just normal fabric. So let's see what happens when I light them. And you can see that the curtain on the right-hand side is burning quite vigorously, whereas the one on the left, you can clearly see the effect of the boron, which is helping the curtains to prevent flaming. I mean, I'm impressed, and I'm a fire safety person.
The boron helps form a protective layer of char, which acts as a buffer between the fire and the fabric. And this charring effect pioneered by Gay-Lussac is used in modern fire-resistant intumescent paint, as Luke is going to put to the test at Edinburgh University's Fire Lab.
And what we're going to do is we're going to subject these two steel plates, which are identical to each other, to the heat from the flame. The plate on the left is coated just with a household emulsion paint, and the plate on the right is coated with a fire protection intumescent paint. All right, so here we go. So the intumescent paint now is charring due to a chemical reaction and swelling and turning into a thick char.
As with Gay-Lussac's boron coating, this charring looks dramatic, but temperature monitoring reveals just how effective it is.
So we've now been heating for about 2 minutes, and I can see that the temperature of the plate with normal paint is at 350 degrees Celsius, and the plate with the intumescent paint is still at less than 100 degrees Celsius.
As the intumescent paint's chemical reaction accelerates, expanding bubbles continue to insulate the plate's surface.
On the left-hand side with the regular paint, the temperature got up to above 500 degrees Celsius, whereas the intumescent paint, it remained about 100 degrees Celsius, so a massive amount of thermal protection for the steel. While it's visually kind of ugly, it's exactly what we wanted to see happen.
In the Gulf of Mexico, the Perdido oil platform has its key components coated in an intumescent paint product born out of the space race. First developed as a protection for spacecraft facing the extreme temperatures of re-entry, it can withstand heats of up to 400 degrees Celsius for up to 90 minutes, along with protecting the rig from saltwater corrosion.
So intumescent paint that we've used on Perdido, it's an epoxy coating on the steel, and if it comes into contact with heat, it'll form a charred layer, and that'll provide a heat barrier between the fire and the steel itself. So the intumescent paint system buys you time to either fight the fire and get it under control, or protect people to the point where if you need to get off the platform and evacuate, you've got that time.
Above all, the platform and its workforce are geared up for stopping the fire breaking out in the first place.
What we do to train our people to combat a fire, it starts with prevention. It's always about prevention, just like you learned in school. Prevent the fire to start with. We do lots of things and work very, very hard to prevent fires from ever starting. We have a ton of monitoring equipment out there to always be on watch 24 hours a day, watching for fires or potential sources of fires like a gas leak.
Perdido is covered by hundreds of sensors and alarms and is fitted with twin 5,000-gallon-per-minute firewater pumps and an automatic foam system that covers the entire platform, including the heliport. All designed to protect the environment, the workers, and this remarkable engineering pioneer. It's more than a century since man first dared to attempt offshore drilling. Now, in 2,500 meters of water in the Gulf of Mexico, a new generation of bold engineers have written the Perdido platform into the record books.
For me personally, that was the single biggest project I had ever worked on. And I'd worked on some good projects, but I have tremendous pride in what we did with Perdido. I think everyone who worked on that project team feels they had done something in the oil industry that had never been done before, and really set the stage to move into ultra-deep water.
By taking history and turning it into high-tech, the team behind the Perdido platform are rewriting the map and exploring brand new frontiers.
What we do is like the space program in the other direction. To be able to push the boundaries of what's possible and achieve more than you thought you could, it just gives a huge sense of satisfaction, and it provides inspiration to the next generation who have to push the boundaries even further than we did.
Engineers have succeeded in making the impossible possible.